Okay, so today we're going to start talking about fluid statics or hydrostatics. Static means that the fluid is not moving, and we're not going to spend a lot of time on static fluids because we're mechanical engineers, and mechanical engineers study stuff that moves. Fluid statics and hydrostatics is a very common area of study for civil engineers. We're studying large bodies of water that are, can be treated essentially as stagnant as far as they're concerned. So they study those a lot. We don't, but we will need to understand fluid statics certainly, and there are a few problems that are certainly relevant to us. So in order to consider this, we're going to consider a little particle of fluid there. It's a delta x, delta y, delta z cube. I've put in my x, y, z coordinates, obviously following the right-hand rule. So x cross y gives you a positive z. And I'm going to do a force balance on this. So if I do a force balance on this little box of fluid, we can just calculate forces on each surface. We'll let P equal P0 at the origin. So we have, that doesn't even matter actually. Let P equal Px, y, and z. So pressure is a function of all three directions. And so we can say that the X force on this little box is going to be the sum of the forces from the two sides of the box. So one side would be this back side here, where the force is going to be pushing the box. Pressure force is going to be pushing the back of the box. Pressure, remember, exerts force only perpendicular to the surface. So it's going to be a pushing force from the back of the box, pushing that little box of fluid to the right. But of course, that's going to be countered by a force on this surface, which is going to be pushing the box back to the left because there's pressure also at that surface. So if we want to calculate the actual pressure, the net pressure, which we will call the total X pressure, X force, we have to consider the pressure at the surface X and multiply that by the area of that surface. So that gives us a force. A pressure times an area always gives us that force. And then that's pushing to the right, so that's a positive. That's the force at position X, which would be here. And then the position at X plus delta X, which is going to be that other surface, this one here, delta X farther away, farther down the X axis, and that's going to be exerting force back the other direction. So that's your net force in the X direction. We know the areas of these. That area there, of course, is going to be just delta y times delta z. And this has exactly the same area, delta y times delta z, because that's the surface area of each of those faces. Obviously, then we can just write that in those terms. So we have f of x is equal to delta z, delta y times px. Minus delta y, delta z, p at x plus delta x. And we can do the same thing in the y direction. It's exactly the same analysis. We have an upward force pushing on that pressure that's at the y coordinate, and then we have a downward force pushing on the surface at y plus delta y. So upward force coming from here on the bottom of the little cube. I'm sorry, y is the surface. Sorry, not the bottom. It's on the back side of this cube, the one we can see. And then a force pushing it back in the negative y direction, which is occurring from a force on this surface that I really can't even show you. It's the one back there, the one directly facing almost directly away from us. And of course, that also, we know the areas for those surfaces are delta x and delta z times delta z. So it's delta x, delta z, times py minus delta x delta z times p at y plus delta y. So that's the pressure force in the y direction being exerted on that little box. And then finally, of course, we can do exactly the same thing in the z direction. Again, now we do have the upward pressure from the bottom of the little cube, A times the pressure at the z coordinate, z position, and then a downward pressure coming from z plus delta z surface. But we have an additional force now because we do have gravity. So we are going to add the body force in. So we have the mass times the gravity, because that's going to also pull our little cube downward. So that's our gravitational force right there. So this is our gravity force. which acts on the body of the cube, hence the mass, the G times M gives you the force, the gravitational force on that cube. So we're going to put that, again, we're going to turn these into delta X and delta Y in this case to allow us to write this in a similar form to the other two. So we have delta X times delta Y times the pressure at the Z surface minus delta X times delta Y times the pressure at the Z plus delta Z surface. So far so good. And then we have the minus mg, but we don't want to use m. We want to use a volume times a density because those are the variables we like in fluid mechanics. So the volume of the cube, delta X, delta Y, delta Z, that's the volume. It could be a cube, could be a parallel pipe head. And then we have the density of the fluid, whatever that is, and then times g. So this group right here, that's simply your mass because that's your volume times your density to get you your mass. So that's our Z force. So we're going to then, for the fluid to be static, so we said it's static. For fluid to be static, that means that Fx equals Fy equals Fz equals 0, right? Because if there's any net force, then the fluid will move. But there's not any movement, so there's not any force. And that means that, if you look at those, if you look at the statement that Fx equals 0, that leads immediately to the observation that Px has to equal Px plus delta x. So Px must equal Px plus delta x. If it's not true, then that fluid would move in the x direction. So the pressure must not be changing in x. So pressure is not a function of x in this problem for it to be hydrostatic. Similarly, the y force also has to be 0, which means pressure is also not a function of y. So there can be no difference between the force pressure at y and the pressure at y plus delta y. Otherwise, once again, the fluid would move in the y direction. In the z direction, however, of course, we're going to get a slightly different result. We have to still have that the z force is 0, but what that means is not that the pressure is not changing. That means the pressure actually has to change. So we have that 0 has to equal delta x, delta y, p at z, minus delta x, delta y, p at z plus delta z, minus delta x, delta y, delta z, rho, and g. So that whole group has to go to 0. And for that whole group to go to 0, obviously we're going to rewrite that and set that all equal to 0 so that we can figure out how p and rho and g are all interrelated. So what I'm going to do this is I'm going to divide by this grouping right here, delta x, delta y, delta z. I'm going to divide the whole equation by that. Of course, 0 remains just 0 on the left-hand side. No problem there. On the right-hand side, I've got p of z now divided by delta z, because the delta x and delta y are gone. They've divided out, minus p at z plus delta z, also divided by delta z. And then the remaining term is just simply rho g. So pretty simple term there. And of course, I'm going to rewrite this. I'm going to say I have this term right here looks like this. So I have 0 equals pz plus delta z minus p of z over delta z. And that's all with a negative sign because that's the negative of what I have. And then I have minus rho and g. So if you look at that of course, I hope you recognize from Calc 1, that is the canonical form of the first derivative. So we're going to go ahead and take that in the limit of delta z goes to 0, limit of delta z going to 0, as this goes to an infinitesimally small thing, we are going to see that, of course, that is the canonical form of the derivative. So we're just going to turn that into a derivative. So we have minus dp dz minus rho g is equal to 0. And of course we can rewrite that as simply dp dz is equal to minus rho g. So what this tells you is that in a fluid that is not moving, this equation has to be true. Otherwise, the forces would not balance and the fluid would in fact move. So this fluid is not moving, therefore dP dz has to equal minus rho g. And we can actually turn that from a partial derivative into a total derivative because we know that P is actually not a function of X or Y. So we said that the pressure was not changing in the X or Y direction. That means that the pressure is only changing in the Z direction. So that's a total derivative. And so that is the governing equation for hydrostatic fluids. And at this point, both density and gravity could be functions of Z. So they are not necessarily constant. But whether they're constant or not, this equation has to be satisfied in order to keep the fluid non-moving.